All right, this is the intro video for AP Calculus BC, section 4.3. We're going to be kind of bringing 4.1 and 4.2 together somewhat here with Riemann sums and what we call definite integrals. So let's just remind ourselves that a Riemann sum is a collection of approximations for area under a curve. And all the different sums we looked at, left, right, midpoint, upper or lower approximations where the base length of all the rectangles is different. These all fall under the category of Riemann sums. So the definition of the definite integral, this is a big one, definitely complicated looking, but what I want to draw your attention to here first is this. We have, in our last class, looked at that a lot, right? Limit as n goes to infinity of sigma from I to n, I equals 1 to n, excuse me, and the argument or the input on the sigma is simply the area of a rectangle. So the delta x would be the base length of a rectangle, and the f of c would be the height of the rectangle. And so the big leap here is that expression, that Riemann sum expression, is equal to this over here, what we call the definite integral. In your book and other books, you'll see this notation over here on the left. I guess partly I want to just show you that this notation really doesn't look the same, but it is the same. Limit is that funny looking triangle goes to 0 and then you see it's that familiar sigma, right? So really, if you look at those two expressions, this that I'm highlighting in red and this that I'm highlighting in red, they're the same. But the limit is very different. So let's talk about what those symbols mean. The triangle with the double absolute value looking thing is the width of the widest rectangle. And of course, f of c is still the height, and delta x is still the base. But let's go back to what this limit means. That limit is basically saying that the width of the widest rectangle, it's also known as the norm of the interval, is going towards 0. So if you think about it, if the width of the widest rectangle is heading towards 0, then wouldn't all the other rectangles have to be approaching a width of 0 as well? So if that's the case, if we have all these rectangles under a curve and the width of them is going towards 0, then the number of them is headed towards infinity, and that's your connection here. That's simply saying the limit as n goes to infinity. So it's really looking at the same coin, just two different sides. Just wanted you to be familiar with both. We'll really mostly be, well, I think only be using this limit, sigma, Riemann sum notation. At least wanted you to be aware of the other one as well. Okay, so we'll fill in some blanks here, kind of explain this already, but if that widest rectangle is approaching 0, the width of each rectangle is approaching 0, this means that the definite integral is an infinite summation of infinitely skinny would be the word I would use there, or narrow rectangles. So this is pretty important. The definite integral is an infinite summation of infinitely skinny items. Since each rectangle is infinitely skinny, informally we are adding an infinite number of heights, right? They're just 1 point wide. Okay, an indefinite integral is a family of functions. We've looked at that. That's of course characterized by the plus c. And then a definite integral, which is what we're talking about here, the definite integral adds those limits. And let me actually erase a little bit here. When I talk about the limits of integration, I'm talking about the a and the b there. So a definite integral is not a family of functions, it's actually just a number. It's going to go with something associated with the area between the curve and the x-axis, and that's what we'll be focusing on really in both 4.3 and 4.4 extensively. So that's it. Hope that was good for you. See you next time in class.